Okay, so today I'm going to work through, I posted a link to this article or chapter from a book, and this is Simulating Blackjack. The book is called Data Science in R, a Case Studies Approach to Computational Reasoning and Problem Solving. And if you click that link that I have on CCLE that takes you to this chapter, you can also click Table of Contents and it will show you all of the other chapters. And I do think it's a great book. You can see how people kind of do data science and think about problems and whatnot. So there's some good examples. I think one of the best ways to learn is to see how experts have done certain things, and you get an idea just by studying the experts. And so if you read, if you have the time, with all of the spare time you guys have, I'm just joking, but if you have time to work through some of those chapters and read through what they've done, I think there's a lot to be gained. In particular, we're looking at this chapter on simulating blackjack because now we're moving into, I guess this week we'll look at simulation, okay? And simulation is a key part of computational statistics in that we often use simulations to answer questions that are too difficult for us to answer directly using analytic methods, okay? And so, for example, the game of blackjack, for those of you who don't know, blackjack is a gambling game often played in casinos, and we can go over the rules and whatnot for how to play blackjack. But, effectively, everything that can happen is based on probability, but it gets quite complicated. Oftentimes at the casino, you're not playing with a single deck of cards, but you're playing maybe out of a shoe of 6 or 7 decks of cards, and things get complex. And a unique thing about blackjack versus other card games at Las Vegas is that they do not shuffle the deck every single game. Okay, they shuffle maybe 6 decks together, and this is called a shoe. But it's basically, you got 52 cards in a deck. You multiply that by 6, so you got what, 312 cards, and then they just shuffle all of those, and then they draw cards and deal out from there. And because they are not shuffling after every game or after every hand, what remains in the rest of the deck or rest of the shoe is affected, or you can learn about the rest of the shoe based on the cards that you have seen played. Okay, so if you've seen a lot of face cards and aces played, early on, you know that in the rest of the shoe, there's not very many aces and face cards left, and vice versa. Okay, and so this is how card counting systems work. Card counting is the idea that you pay attention to the cards that have been played. Based on the cards that you have seen played, you try to guess what kind of cards are left in the deck, and based on what you know about what's left in the deck, you alter your bets. You either bet more if you believe what's left in the deck is in your favor, or you bet less if what's left in the deck is not in your favor. Okay. Now, card counting is not illegal, but it is discouraged, and the casinos reserve the right to kick you out and ask you to stop playing if they believe you are counting cards. But if you ask, is it illegal to count cards, they'll kind of hem and haw and say, no, it's not illegal, but it's discouraged. Okay, and you obviously don't want to dramatically make it obvious that you are counting cards by significantly altering your bets and things like that. But people have tried to study, what card counting systems work well and things like that. Do they actually make a difference and things of that nature. But as soon as you start trying to do the math there, it gets really complex, okay? And so maybe a better way to answer these questions is via simulation. And so we can set up a computerized model of playing blackjack, and then we are also able to implement a card counting system in this computerized model, okay? Now, we'll try to work through the text in this thing, and I'll kind of explain exactly what, and this chapter is written by Hadley Wickham, so it's high quality stuff, and I'll try to explain, the stuff that he goes through. We might run out of time, and you might have to study things on your own a little bit. I'm not going to test you on this, but I think it's a good case study of writing a well thought out simulation. It uses some object-oriented stuff that we've learned, like reference classes and things of that nature, and we can see how we can start to answer questions about these complex things that that involve counting cards, playing blackjack, and things of that nature. Okay, so well, first of all, let me just kind of explain the game of blackjack. Maybe let's find a deck of cards. Okay, all right, so this is what a deck of cards looks like. There's 52 cards. You shuffle them up, okay? And in blackjack, all of these cards, these 16 cards, 10, Jack, Queen, King, okay, of which there are 4, these are all worth 10 points, okay? So all the face cards are worth 10 points, and the 10s themselves are worth 10 points, okay? And these ones over here, they are all worth their number, 2 through 9, okay? And then the aces are worth 1, or they're worth 11, okay? And the goal is to earn as close to 21 points without going over, okay? And the best way to get that is to get a 10 and an ace. That's worth 21. That's called a blackjack, and you actually get a bump. If you get 21 points via a blackjack with only 2 cards, it actually beats getting 21 with 3 or more cards. So if you get like a 10, an 8, and a 3, that's also worth 21 points. But the 10 with the ace will still beat the 21 the other way. Okay. But anyway, you want to get as close to 21 without going over. If you go over, your hand will automatically lose, okay? So if you go 10, 8, and 4, that's 22 points, you lose automatically, okay? That's called a bust. And basically, when you play the game, the dealer will deal 2 cards to you. The dealer deals 2 cards to him or herself, and shows one of their 2 cards, okay? So you see one of the dealer's cards, and you have to try to guess what the other, well, you don't have to try to guess, but that one card that the dealer is showing gives you some insight about what their hand might be worth. So if the dealer shows a 5, okay, then at best, their card hand is worth 16 if they have a 5 and an ace. Or they might have a 5 and a 2. Okay, so that you know that they have somewhere between a 7 and 16 points or something like that. Okay, you can kind of guess what they have based on what the dealer has. What you think the dealer has will affect the decisions you make. So if the dealer is showing a 5 and you've been dealt, let's say, a 10 and a 7, which is worth 17 points, you may opt in that situation to stay. Okay. Stay means you are going to keep the cards that you have and not take on any additional cards. So in that case, you have a 10 and a 7, you have 17 points, and you're going to take your 17 and face them off against whatever the dealer has. Okay, and the dealer will choose to either hit, which means take on more cards, or stay, or whatever. They have to follow certain rules. And And that's how the game goes. You're dealt your 2 cards. You can choose to hit or stay, which means either take on more cards or keep the cards that you have. After you choose to stay or stand, stand, you take your point total, compare it to the dealer's point total. Whoever has more points wins. Okay. And whatever you bet, you get that much money back. So if you bet $10 and you win, the casino will pay you $10. If you lose, the casino keeps your $10. Okay, so it's blackjack's always an even money game. Well, usually if you get blackjack itself, meaning you get the ace and a 10, they'll give you 1.5 times your bet. Okay. Only play at a casino. Only play blackjack at a casino if they offer the 1.5. If they're not, they're shorting you and they're keeping a larger margin. The casino's edge comes from the fact that you have to make all of your decisions before you get to see what the dealer does. So you have to choose to hit or stand based on incomplete information, and you're always at a greater risk of busting if because you have to make all of your decisions first. Okay, so if you bust and then the dealer also busts, you still lose your money. Okay. Okay. I don't know if that made any sense, but that's the game of blackjack. We'll kind of go over the rules a little bit more as we go through the simulation and whatnot. Okay. So to start off with the simulation, we're going to first create a deck of cards, okay? And in blackjack, only the numeric value matters. It does not matter the suit of the card. So if you've got aces, hearts, or spades, that doesn't matter. It's just whether you have a 5 or a 9 or a 10 or whatever, okay? And so in this case, we can create a deck, which is represented by 1 through 10, ace through 10, and then jack, queen, king. So that's 13 cards here, and we're going to repeat that 4 times. And so if we look at our deck, this is what we have. We see all 52 values laid out here, and that's what we have. And then here, in the beginning, we're going to implement kind of a simplified version of blackjack where we are shuffling the deck with every single game. Okay, only later will we worry about implementing the shoe. Okay, so in this case, we're going to create a function called shuffle decks. Okay, and the way shuffle decks works is it just takes from the deck, and we're going to sample. The function sample here is sample without replacement, and that's all we're going to do. Okay. So if I do shuffle, shuffle decks here is going to, you're shuffling 1 deck or you're going to shuffle like 5 decks. Okay, so if I do shuffle decks 1, this mixes up the 52 cards in a deck. If I say shuffle decks 10, this creates, here we've shuffled 10 decks together. Huh?
That's gross.
10 decks? Yeah, it's a lot. Okay, but probably, it's a lot of casinos probably use a 6-deck shoe. Okay, and this is what we get. Okay, and so in the beginning we're getting a bunch of 10s, but as the game plays out, we might get an assortment, and because it's shuffled, who knows what's going to happen. Okay, now we want to create a function that is going to calculate how much our hand is worth, okay? And so our hand value is going to be a function of the cards that we have in the hand. In the most basic case, we just take the cards that we have and we add them up, right? But there are a few special cases. So if you have an ace, that card might be worth 11 or 1, okay? So, when we, let's say if I do let's just call this my shoe, and then for the shoe, this is not really my shoe, but let's say, you know, I'm just dealt these two cards, okay, a 10 and a 10. So in this case, it's worth 20 points. But if I do, I don't know, cards 10 and 11, okay, 18 points. Yeah, let's, I don't know where I'm going here, but okay, so in this hand, if I have if I'm dealt the third and fourth card in the shoe, okay, I have a 1 and a 6. So if I just told my hand value calculation is just add those two values together, it would calculate my hand value as 7, which is technically okay, but in blackjack you would never say, oh, this is worth 7. You would say this is worth 17, okay? And this is known as called a soft 17 in blackjack. If your ace counts as an 11, it's called a soft 17 because if you say hit and they deal you another card, let's say a 6, okay? 17 plus 6 goes to 23, but because it's an ace, you don't bust. That ace changes from 11 points to 1 point, okay? And so now you have a 1, a 7, and a 6, and that's worth 14 points, right? 1, 7, and 6, yeah. Or third.
Because there's 1 and 6, and then another 6.
Oh, okay, yeah, I'm sorry. Yeah, 1, 6, and a 6. So if you're dealt a 6, it's going to be worth 13 points instead of 23, okay? And so this would be considered a soft 17, if that makes sense, okay? Versus if this were like, if you had 4 and 7 and 6, okay, that adds up to 17, and that's a hard 17 because if you're dealt another 6, you lose. You go to 23, 4, 7, 6, and 6. That's 23, and you can't say like, oh, I want to make, I want less points or something, okay? So this would be known as a soft 17. Okay, so anyway, what we have to do is we have to say we're going to check for an ace and change the value if it doesn't bust. So if any of the cards are equal to 1, which is what we have, and the total value right now, which is calculated as the sum of the cards, is 11 or under, we can add 10 to it, okay? And if that's the case, our value is going to be value plus 10, okay? On the other hand, if our value goes over 21, we're going to say this is a bust, okay? And we're going to set our hand value to 0, okay? Because the way we're going to determine if we won or not is we're just going to compare one hand value to another hand value, and whoever's higher is the winner, okay? So we're going to say if you bust, your hand is now worth 0, and that's always going to lose, okay? And then lastly, if you have 21, so if the sum of your cards is 21 and the length of cards is 2, meaning you got 21 points with 2 cards, which is only possible with an ace and a 10, then we will say this hand is worth 21 and a half, meaning you have a blackjack, which will edge out other hands that are worth 21 but with like 3 cards or something like that, okay? And lastly, we're going to return the value, okay? So these are all this is basically return 0, return 21 and a half, or return whatever value that we have, okay? So this is hand value, and we can kind of test this out. So if I say hand value, so my first 2 cards, if I did shoe 1 through 2, that was 10 and 10, I can just say, okay, hand value of shoe 1 and 2, whoops. Oh, there's a capital V in value. Okay, it's worth 20, and then the 3 and the 4 was the ace and the 6. Okay, it calculates it as 17. I can kind of see what happens if I do 1 through 3. Shoe 1 through 3 is worth 21 points, which is correct. Okay, 10, 10, 1. It's a very risky to ask for a hit on a 20. You would never do that. Well, I don't know. Unless you were trying to lose. Okay, so that's what we have here. Okay, so we have the hand value function to calculate the way the way we go. Okay, and now we're going to create a function that's going to tell us how much we win. Okay, and this is going to be winnings. And so this is going to take the dealer's value and the player's value. Okay, so what's going to come here in the function is we're going to do hand value based on the dealer's cards. So we have a value for the dealer and we have a value for the player, and then we compare basically whether what we win or what we lose. Okay, so basically if the dealer so these are all of the cases here. Okay, if the dealer has over 21, which means the dealer has blackjack, then we would tie with players with blackjack. Okay, so it's not explicitly clear, but what happens is that if we don't, so you have to keep in mind how R coerces values of true and false to 0 and whatnot, right? Okay, so we're going to look at this statement, players less than or equal to 21. So if the player has anything other than blackjack, right? So if their hand value is 0 up through anything to 21, okay, they are going to lose. So this will get coerced to a 1, okay? And 1 times -1 is -1. So their winnings will be -1 times their bet. Okay, so that means they've lost their bet. If the player has blackjack, which means their player's hand is worth 21.5, what is the value of this statement? This statement will be false, which will be a 0. Okay, and then so their winnings will be 0, right? If the dealer has blackjack and the player has blackjack, then it's called a push. Neither side wins. You know, the $10 you bet, you just keep. You don't gain anything, you don't lose anything. That $10 just stays there, and so that's what happens there. All right, is that okay? The logic of this statement. Okay, this is just kind of like a concise way. Hadley even writes even more concise, but okay. Let's take a look at this. If the dealer busts, okay, if the dealer equals 0, then that means all non-busted players win. So okay, so all players who didn't bust will win. So if you have blackjack, then you'll get 1.5. If you have anything between this is greater than 0, meaning between 1 and 21 points, then you win 1. Okay, but if you bust, you still lose. Okay, you still get -1. Okay, so if this is true, then you'll get this. So these are all true-false statements, and you know, in each of these cases, you can check only one of these things will be true. If this is true, then these are both false. So you have basically a 1, 0, 0. So we're just adding these all together. Okay. Does that make sense there? Okay. And then lastly, if the dealer has 21 or below, then you know, the player values that are greater than the dealer will win. Okay. So if the player has blackjack, they get 1.5. If the player is less than or equal to 21, and the player is greater than the dealer, and then that's going to be a win. But if the player is less than the dealer, then they lose. Okay, so that's what we have, right? So this includes the case where the player busts and gets 0, right? Okay, so this is the winnings function. There's another concise, even more concise way, and this is just another way of true-false. So if we have all of this, then you either win or you lose or things like that. Okay, so this is, you know, true, false, things like that, and you'll either win or lose and things like that. You can take your time to check this out. Okay, so that's the winnings function. So basically, we can just do winnings. You know, if the dealer has 20 and I have 20, what happens? The winnings is 0. Okay, if the dealer has 20 and I have 19, I lose. If the dealer has 20 and I have 21 and a half, you know, I win blackjack, something like that, okay? If the dealer has 0, if we both bust 0 and 0, I still lose, okay? So the winnings kind of tells you, you know, you give the dealer's hand value versus your hand value, and it will tell you whether you win your bet or lose your bet or something like that. All right, is that okay? All right. Whenever you do a simulation, it's always a good idea to make sure your code behaves the way you expect it to behave, okay? And so here we're going to do a little bit of testing, okay? And so here we're creating a list of different hands. And we want to just kind of make sure that all of these things take on the proper value, right? So 10 and 1, this is blackjack, and we should make sure that this returns the proper blackjack value, 21 and a half, okay? And here we're just kind of testing out different cases and saying like, okay, 10, 1, and 1 should add up to 12, okay? And in these cases, you know, 7, 6, 1, 5 should be 19, 3, 6, 1, 1 should be 21. And so these are just a few different test cases. And we could kind of test these out ourselves. We can just do hand value, and we could do 10, 1 and see how it goes. We can also just kind of feed it in through using you know, a few options, okay? So one, you know, we could use the apply function, right? We can say sapply. Sapply is apply the function to a list or something and simplify it, okay? So normally when you feed in a list, you would use lapply. Lapply, you feed it in a list and it returns a list. What sapply does, the S means simplify. Generally, you'd feed it in a list and it does its best to return a vector or some kind of simplified form, okay? So in this case, if I do lapply test cards, which is my list, and I apply the function hand value, it's going to return a list of the hand values, okay? And sapply just takes the same thing and then it simplifies it to a vector. That's what we have, okay? So this is, and I'm going to test to see if this thing is the same as the vector of card values. So looking at this, I say, okay, these are what the card values should be. Test cards underscore value, and then I just see is indeed, are these two things equal to each other? Okay, now on visual inspection, they do, and we can also just say, are they identical? Yes, they are. Okay, so so this is a way to kind of run some test cases. And you know, if you think of more test cases, you can add them here and add the value down here, and you can kind of do run all the test cases in just one line. Okay, the hardest part of running test cases is kind of keeping track of all the test cases that you want to do, and making sure you run it every time you update the function. Okay, if you so let's say I wanted to try out the other winnings function, because right now my winnings function is the long, this earlier code. If someone else comes along and says, I wrote this winnings function, right? And so now I check out, okay, what is my winnings function? It's this shorter thing. I can still run the test code, all the test cases, just to make sure that the thing works like I expect them to. And I don't have to feed in every single one of these cases. I can just run this one line of code and it says true, so then I know that it's working. Okay? I don't have to run through every single individual scenario. You could, if you only have like 3 test cases that you want to test out, sure, you can do that. But it probably makes sense to make your life easier in these cases, okay? All right, and then the other function that we want to test is to see if the winnings function works. Okay, so this test case, this testing was to make sure that the hand values were calculating the values of the cards correctly. And over here, we're now going to test to see if the winnings are correct, meaning if here are a few scenarios, okay? The test values are, the player, a bust, 16, 19, 20, 21, 21 and a half, which would be the blackjack. And it's just saying who's going to win and what are the winnings here, okay? So here we created a matrix, okay, called test winnings. And this is what the matrix looks like. And this is, and if I add the dimension names, this is what the matrix looks like, okay? So this is something we created manually, and this is, according to our understanding of the rules, if the player has 0 and the dealer has 0, the player's winnings would be -1, okay? And if the player has anything other than 0, they would win, and if they have blackjack, they should get 1.5, okay? And so this matrix represents what should happen in each of these cases if the player has this hand value versus the dealer has this hand value, right? So if the player has blackjack, they should win 1.5 in every single scenario unless the dealer also has blackjack, and in that case, it's a push. Okay. Okay, so this is what we are expecting. These are the results that we expect to get. And then now we're going to clear this out. Okay, so check is now an empty matrix. Okay, so what we did here is we just duplicated test winnings to check, and then check with the empty brackets means all values in the matrix. We cleared them out to NA, right? Okay, and then what we're doing now is we're going to run a loop inside a loop, okay? We're going to say, okay, first go from, for each of these values and test values, and then fill in the spot ij what the winnings will be in that case. Okay, so it just, it's a 6 by 6. We're going to run this for all 36 values. We fill this in, okay, with check. Did that make sense, this line of code here? Or this little chunk of code? This is to fill in the matrix check. So we're going to run that. We fill in the matrix check. This is what we have, okay. R is the matrix that we've run. Check, is that identical to what we're expecting, which we programmed ourselves or wrote ourselves with test winnings? They are indeed identical. So we have that statement true there. Okay. All right, so it looks like our hand value and our winnings function is indeed working. And so now we can start to implement the actual gameplay of the game itself. Okay, so the first thing we need to do is implement a way to deal cards. Okay, and what we're going to call this function is going to be called shoe. And in our case, what the shoe does is it's going to take our deck and we're going to just deal them out. And so this shoe basically we shuffle our hand every time we do a new hand here. Okay, so let me just kind of show you what shoe does. Okay, so if I run shoe, it's just returning a random card here. Okay, and if I say deal out 10 cards, it's going to deal out 10 cards here. Okay, so that's what we have. So the shoe is dealing cards with replacement. Okay, so it's technically not accurate because it's saying we're taking our deck of 52 cards, we deal one out, and then I'm sampling with replacement. So it is technically possible to be dealt. If we were keeping track of what the ace of spades was, it's possible to get dealt the ace of spades twice because it's with replacement, right? So this is not the most accurate simulation of the game at this point, but it will work for now, okay? In the beginning, we just want to get the idea of dealing out a blackjack hand working, okay? So the shoe deals with replacement from the deck, okay? And then we're going to create a function called new hand, okay? New hand is going to create a list, and the list contains 3 items: the size of our bet, the function shoe, okay, and the cards, which is the 2 cards that we are dealt, okay? So the hand itself is a list that contains the function for drawing cards, okay? So keep that in mind. The hand tells us about the way we are getting new cards, okay? And so the default values for new hand will be, we have to specify how we're getting our shoe, okay? And it's going to take 2 cards from the shoe with a bet of 1, okay? So let me just do new hand, okay? And then the only thing I need to specify is shoe. So shoe itself is going to be shoe, okay? And so here I've got, what I return is a bet of 1. The cards are 10 and 3, and then it also contains the function for drawing new cards, okay? Which is just drawing with replacement here. Okay, what am I doing in the next line? Okay, this in line 94 I have dealing a new hand. In line 98 I have pretty much the same thing, except I put in this thing called structure. So what is that going to do? Huh? Yeah, now we are giving it a class, meaning this is now an S3 object. Okay, so now we're doing a little bit of object-oriented programming, and so we're going to have a class called a hand. Okay, so I'm doing new hand, and so when I do new hand, and if I call new hand on shoe, it does the exact, it gives me pretty much the exact same thing back, okay, except I've got different cards now, and then it has the attribute hand. Okay, so this is now a list with the attribute of class equal to hand. Okay, and all we're doing now is now we can implement a print function specific for hand. Okay, so we have a print method for objects of class hand. So now that we have this, we can say, instead of when we look at our new hand, instead of printing it out like this, telling us the exact function of the shoe, I don't actually care about that. I just really want to know what my cards are, maybe what my bet is, okay? And you know what would be helpful is if I knew how much these cards are worth, what the value of my hand is, okay? And so when we say print.hand, it's going to give out the custom print method, okay, which is going to say you've got a blackjack hand. We're going to paste our cards, okay, and separate them with a dash, okay. We're also going to use the function hand value to calculate the values of our cards, and then we'll say how much our bet is worth. Okay, so let's just kind of take a look at this. Here I'm going to create a new hand with a bet of 7 using the specified shoe, and then when I ask print out my cards, instead of printing kind of the old way, when I call my cards, it prints it out nice and nicely. Okay, it says blackjack hand, you've been dealt a 10 and a 9, which is worth 19. The bet is 7. Okay, I could go back to print.default and ask for what my cards are worth, and this will print out the old, the old-fashioned way. But I think, having our own print method for objects of class hand definitely make our life a little bit nicer, right? Okay, so we've implemented our print method so that we can take a look at cards. And so, I can deal myself a new hand. And so in this case, I got dealt an ace 10, and it calculates the value as 21 and a half, right? And if I deal myself a new thing here, you know, I got delta 3-2, which is, you know, not that great. Okay, 6-3, and so on and so forth. Okay, so here are just different hands that we're dealt, and we can see the way they look. Okay, so we have a way to deal out new hands, and now we need a way to actually play the game, right? And so we have a few options. We're going to say, okay, what happens if a player asks to be hit? Okay, meaning they're going to take the current hand, and we're going to deal a new hand, a new card, right? So what is this going to do? We're going to take, so hit is going to be a function which requires a hand object, and the hand itself is a list. And so what hand cards does is it says, okay, deal yourself update the cards by taking your current cards and adding one card, right? And because hand itself contains the function shoe, we can say draw one card from the shoe. Okay, and so hit updates the cards in the hand as such, and then it returns the hand. Okay, so we can kind of just take a look. So let's just take a look at my cards. So currently my cards is a 6-3, which is worth 9. And we're going to say, okay, hit my cards, okay, and I got delta 10, which is like the best case scenario, and so now my cards are worth 19. What I should do is I should save the output of hit and update my cards accordingly, right? Because right now my cards are still, oops, 6-3, and if I hit, you know, I could get different things. Oh, I guess the best case scenario is actually getting dealt an ace and being, you know, having a total of 20, but things like that. Okay. So that's what we have. We'll create a function called stand, okay, which basically takes your current hand and does nothing to it, and it returns your hand. Okay, now it feels a little silly to do that, but we're going to just create this function at this point so that when we implement kind of an automated strategy thing, we can just say hit or stand without having to do things. Okay, so if I take my current cards, my cards, and I say stand, this does absolutely nothing to it. It returns the exact hand that I have. Okay. Okay. In Blackjack, there's something called doubling down, right? And maybe you heard this term used in a context outside of Blackjack, where someone says, you know, I'm going to stick to my current strategy, as good or bad as it may be, and I'm going to just kind of dig my heels in. Doubling down, you generally, you know, casinos have different rules about when you can double down, but in general, you know, if you are dealt a 10 or an 11 or something like that, so you got dealt a 6 or 5, double down says, I'm going to ask for one more card. You ask, you hit, and then you say, whatever card I get, I'm going to stand after that. I'm going to take my one card and stop playing, okay? Because normally when you hit, you have the option to hit again in the future. Doubling down is, I'm going to take my cards, hit once, and that will be whatever card I get, I'm going to stop, okay? So, and the benefit of doing that is that you get to double your bet. So whatever, if you bet $10 originally, if you double down, you have to put another $10 on the table. Okay, so now you bet a total of 20, and then you know you win or lose based on that. Okay, so in this case, the function of double down takes your current hand, it updates the bet by doubling it. It updates the hand itself by doing hit, by hitting the hand, and then finally you stand, which will return the hand itself. Okay. So we're building up our functions by kind of incorporating our other functions. We don't have to say, okay, well, what does hit itself mean? We have the hit function, so we're saying we're going to run that, and then we do this. Okay. So double down, We do that? Okay, so if we take a look at my cards right now, it's still that 6-3 hand, and if I double down, we're going to take on one more card, whatever that is, and my bet is doubled, okay? So I got a 6, now I'm stuck with 15, which means I'm almost guaranteed to lose, and my bet is now $14, okay? So there we go. Is that okay? All right, and then the other thing you can do in blackjack is you can split a pair, okay? A lot of times casinos will only let you do this if you're dealt a 20 or a 16, like you're dealt 2 8s or you're dealt 2 10s or something like that. Sometimes some casinos will let you do it in other cases. Here we're going to pretend it like they'll do it in any case, okay? We don't even have a check to make sure it's a pair. We could do that. We could say run some kind of check where split pair is only allowed if the hand itself contains a pair. But the idea is, let's say you are dealt 2 8s, okay? I'm sorry, casinos won't let you split a 20, I'm sorry. If you're dealt 2 8s, your hand is worth 16, okay? And in blackjack, 16 is considered like the worst possible hand you can get, because as far as the rules for the dealer is the dealer will continue to hit until they reach at least 17. And if they hit 17, then the dealer has to stop hitting, okay? Which means if you're dealt a 16, you know the dealer will continue to hit until they're over 17, and the only way you can win with a 16 is if the dealer busts, okay? Which happens, you know, a lot, but it's also kind of the worst position to be in. So a lot of times what the casino will let you do is it takes your hand of 2 8s and then you split it. You have to, you know, if you bet $10 on the original hand, you have to put forth another $10. So now you have $20 on the table, but you're playing 2 hands simultaneously. You have one hand that has an 8 and another hand that's an 8, and the casino deals another card for each of those things. So now you might get an 8-10 on one side and an 8-3 on the other side or something like that, okay? And so the way we're going to implement this is when we split the pair, we're going to get back 2 hands. And so what it's returning, so the function, there's only one thing here, which is what it returns, which is the list. Okay, it's going to return back a list that the list contains 2 hands. Okay, 2 new hands. The new hand will have your current shoe, which is the function on how to draw cards, and then the cards that will be dealt will be the first card in the hand plus a random card from the shoe and the bet, and then the second hand has the same thing, except the first card in that hand is the second card in the split pair and something from the shoe. Okay, so we're going to run this. Okay, whoops, that's the wrong button there. Okay, and so if I take a look at my cards, I technically cannot run split pair on this. If I try to say split this at the casino, they will just say no, because this is not a pair, right? It's 6-3. But the way we implemented this function doesn't actually check that. So I can just say, okay, split this hand, and we see that it does that. Okay, it takes the first card 6 and it returns my first hand. Okay, and then it deals on a 10 there, and then it takes the 3 and it comes over here and it deals it over here. Okay. Most casinos will only let you split once. I don't know if I guess technically we could take back, here, let me do split hand and just save this. So here, I got dealt new things, okay? And if I do split hand, technically, I might even be able to take this and run split pair on this, okay? And forever, continually do this. In the casino, it won't let you do that. Okay, So let's try this out. Here, just set a seed here. We're going to deal a new hand for the dealer, deal a new hand for the player. Okay. Let's see what the dealer shows. The dealer is currently showing a 5. I currently have 6-9, which is worth 15. Okay. So what do I do? If the dealer shows a 5 and I have a 15, maybe I want to hit my hand. Okay, so we will update by hitting my hand. Okay, let's see what I have. I got delta 1. Okay, so I have 16. Maybe I will just kind of stop there. Let's see what the dealer has. The dealer has 5-5, a 10 points. The dealer hits. Okay, the dealer has 20. Okay, and then so my 16 versus the dealer's 20, I lose, and we can just kind of say winnings of the dealer's cards versus the player's cards, and we can see that I lost in that case. Okay, here is a function to program what cards the dealer is going to have. Okay, so the dealer cards will be the dealer's first going to get 2 cards from the shoe, and then it says while the hand value is less than or equal to 17 and hand value greater than 0, meaning if the dealer has less than 17 and the dealer has not bust, we are going to keep drawing cards from the shoe. Okay, so we keep drawing cards from the shoe until either one of those two things happens. The dealer gets 17 or more, or the dealer busts. Okay, and when we're done with that, return the cards that we have. So here we program this function dealer cards. Okay, and so we can say dealer cards. Okay, and then we'll give it the shoe, and then so in this case it goes 10-3-10, so the dealer busts in that case. 2-7-10, and the dealer stops at 19. 2-4-8-10, so this was 6. 14, 10, 24, the dealer busts, so they stop. 8-4-8, the dealer gets 20, and they stop. Okay. Okay. And now, because the goal is to have an automated way to play blackjack, we're going to implement simple strategy. Okay. And the simple strategy is this. You look at the card that the dealer is showing face up. Okay. And if I bust, then I'm going to stand. If the hand value that the dealer has is greater than 6 and mine is less than 17, then I will hit. Okay. So if the dealer shows a 7, 8, 9, or 10, or an ace, or no, just 7, 8, 9, or 10, and my hand value is under 17, I will hit. Okay. Otherwise, I will stand. So if the dealer shows a 5 and I have 13 points, in that case, I stand, because what I'm hoping for is the dealer has a 5, which puts them in an awkward position and that they're going to bust. Okay, so the simple strategy will just kind of tell us what we should do. All right, so simple strategy here. Let me just kind of implement this. Okay, and so we will see what we have. Or another way to play is to prompt the user itself. We can say the dealer shows this current face-up card. This is what you have, and what do you want to do? And you can ask, you know, stand or hit or something like that. Okay, so that's a prompt user. Okay, and so the automated game itself is right here with play hand. Okay, with play hand, we have to give it a shoe, the strategy, whether that's the simple strategy or whether we are prompting the user for what to do. Okay, In the automated case, we're going to give it the simple strategy, something where it's not prompting the user. Okay, and then it's going to deal out two hands. One hand for ourselves using the new hand function, and then the dealer, which will have the dealer's cards using the dealer's cards function. Okay, so this is what we have for playing a hand. Okay, we're going to take the first card that the dealer's dealt as our face-up card, and then the action that we do is going to be determined by our strategy. Okay, whether we stand or hit or double down or whatever it might be. Okay, and so we are going to, because it's automated, we are going to run this. Okay, so if the action says hit, then we hit our hand. Okay, and then we have to call the strategy on itself again. Okay, because after we hit, then we have to say, okay, after you hit, are you going to stand or hit again? Okay. Otherwise, you know, we can double down. If the action says to double down, we can say double down, and then the next action will be stand. If we get anything other than that, we're going to say we get it. It's going to kick back an error. Okay, and then it says, you know, and we're going to repeat this process as long as the action is not stand, and as long as our hand values hasn't bust. Okay, and then at the end of all of that, the only thing we really care about is our winnings. Did we win? Okay, and we're going to take our winnings multiplied by our hand bet. So the only thing that play hand returns is it's going to return whether we won or lost. Okay, so here I'm going to do set my seed, and we're going to hit play hand, taking the shoe and our simple strategy. And here we won. Okay, that seemed unexciting. So what we can do is, you know, somewhere along the way, if we want more than just the winnings, we can kind of have it print out a bunch of stuff, right? So we can modify, we can say the hand, when we do play hand, we can add kind of some lines that kind of print out what exactly we have, and we might be able to see what exactly is going on. So what we can do is we can do print hand and print dealer. Okay, and maybe maybe we'll get a sense of what it is doing. Okay, so we can do this. Oh, wait, did that not? I guess. Let me do print hand here. Let's see if this does anything. Okay, so in this case, we got dealt a blackjack hand. The dealer has, you know, started off with 5, you know, 5, 5, 6, 9, and kept going. Okay, and maybe if I play again, 2, 7, and so we can kind of see a little bit of what happened here. I guess we took a look at the dealer hand. Oh, it didn't actually show what gets printed out at the bottom, but I guess in this case the dealer bust, and so we win with 1. Okay, but yeah, pretty much play hand just is going to return whether you've won or you've lost. Okay, and I know this is not very exciting, but this is effectively what we're trying to go for. We're trying to get an idea of whether we are winning or losing or whatnot. Okay. Here we are giving oh, this actually solves the problem that was going on, is we didn't know what was happening, so we can give it the option of verbose equal to false or true, okay? And in this case, if verbose is true, it's going to print out the action that we took, and it's going to print out, other stuff, okay? So in this case, we can do verbose equals false or true, and so in this case, with verbose set to true, we can see what the dealer has and what the player did, and what we have here. Okay, so if I want to play again, the dealer has this, and this is what we did, and so kind of our verbose actions show us exactly what we did. So we did, we first hit, and we ended up getting 3, 10, 10, so we lose there. Okay, the dealer has 20. We ended up with 10, 3, 2, 10, 0, and we lost. And if we kept playing, the dealer got 0 and went up. Okay. Okay, and then the last thing is we wanted to implement the split pair functionality. Okay, so this is kind of the most complex of this, right? So everything else is the same. Is we've got stand, hit, double down, and then finally, if we have split pair, what we're going to do is we're going to recursively call play hand on the two functions, on the two hands itself. Okay, so after we split a pair, remember, splitting a pair returns a list of two hands, right? So after we call split pair, then what we do is we're going to recursively call the function play hand on each of these things. We're going to say play, run the strategy on the first hand and run the strategy on the second hand, okay? And then at the end of split pair, what we're going to do is we're going to add, so when you play hand, what it returns is whether you won with a 1 or you lost with a -1 or you had a push with a 0. It's going to return basically your winnings, and we add those two winnings together, okay? And then it returns basically the winnings that you have. So that is the play hand function with split pair implemented there. Okay, if you guys are following along, and so we can kind of just see what happens here. So in this case, we do this. We can prompt the user and things like this. So the dealer shows a 10. You have 2, 7. You have a 9. What do you want to do? We want to, in this case, we're going to hit. Okay. So we hit. The dealer shows 10. Now we have 19. What are we going to do? We're going to stand. Okay. And the dealer busts, and we win. Yay. Okay. So that's what we have. Okay. We can. Okay. Dealer shows 2. We have a 12. So what do you think we should do? Okay, so what we're going to do is we're going to stand. Okay, now we might lose, okay, but we're hoping that the dealer busts, which is what happened, right? So we have a 12. The dealer started off with a 2, 4, a 6. They dealt themselves an 8, which took them up to 14. Because of the rules, they have to deal themselves again, so they take a 10 and they bust, and we win with our 12, which is about as good as we can hope for. Okay, dealer shows an 8, so we have to kind of guess that they have a 18. We have a 13. We're gonna have to hit. Okay, so we ended up busting. Okay, so we lose. Okay, but yeah, this was hopeless. Okay, we had no chance of winning either. If we stood. Is that right? Past tense of stand for blackjack, is it stood? Yeah, well anyway. 13 we would have lost, 23 we lost. So this was a situation where there was no win, okay? So anyway, that's what we have. We have the simple strategy, which was either hit or stand based on those simple rules. Blackjack has long been studied. You know, anytime there's money involved, people study it, right? So, you know, if you go to Blackjack on Wikipedia, you know, it has all the rules explained here. They also have the exact strategy of what to do if you're not counting cards, okay? Which is what you're not supposed to count cards, right? And so it says if this is what you have and the dealer has this face-up card, what should you do? You should stand in these cases, or you should hit, or you should double down if you're allowed. If you're not, take a hit, things like that, right? And then, you know, you got the soft totals, which means you have an ace in something, or something like that, right? Or if you have pairs, you know, when you do, you either split them or whatnot, right? So if you have a pair of aces, I'm sorry, that's when you're supposed to split them, or a pair of eights if you're allowed, things like that, okay? So this is the optimal strategy with no counting of cards on what you should do for blackjack, right? So if you go to the casino and they have like the video game, right? You can have this in your little pocket and play this, and you know you'll have your lowest loss rate, expected loss rate, which but because of random chance, you might lose a lot quickly. Okay, and I have this uploaded to CCLE in a file called strategy.csv, and I can load this up here. And if we take a look at the lookup table, this is what we have. We've got you know, either a hard total or a soft total, and then it has what you should do, stand or hit or whatever. Okay. Okay, and then so what we have here is we have a new function, not the simple strategy which just returned stand or hit, but here this is a function that's going to use this table to look up exactly what we should do. And you know, I think for the interest of time, I'm going to kind of glaze over this. But basically, it's going to take your hand, the dealer's face-up card, and take the lookup table that we have, and it's going to just look up exactly what you have. And based on what we have here, we are going to what it returns is it's going to find, you know, it's subsetting the lookup table based on your value and the dealer's value. Okay, and you can kind of go through and just double check and make sure that it is correct, but it's written correctly here. Okay, so this here, lines 301 through 332, is an implementation of the ideal optimal strategy. Okay, and so we can see, okay, what is the optimal strategy if you are dealt a 4-1 a 6? Okay, right? 4-1 6. That's, how much is that worth? That's worth 21 points, and the dealer is showing a 3. Okay, and in that case, we should stand. Okay, optimal strategy 3-2-6, which is 11 points, and the dealer showing a 3. We should hit and things like that. Okay, and so here this is stop if not. This is a way to just run a bunch of test cases. And we can see, okay, is this returning what we do? Okay, so if we run this, oh, it says there's an error, strategy optimal 61516 equals H is not true, right? 61516, right? So what is this? This is a 6-1, I don't know, what is this? This is a hard 13. If 6 plus 1 is 7, plus 5 is 12, plus 1 is 13. It's a hard 13, and the dealer's showing a 6. It says hit is not true. We can go back to Wikipedia. So we have a hard 13, the dealer's showing a 6. Yeah, we should stand in that case. All right. So let me fix this. This should be a stand, okay? And we run through it, okay? And then it didn't return any errors. So that means everything is programmed correctly. So my test cases were actually, there was a mistake in that 6151 adds up to a hard 13 with dealer showing 6, you should stand in that case. Okay, and so we can kind of see this. And so now that we have play hand, we can give it the shoe and the optimal strategy, and we can just kind of see what happens, right? And so here we are implementing the optimal strategy, and we can see the different things. And so now when we play with the optimal strategy, we have options like doubling down, so it is possible to win 2 rather than winning 1, okay? Okay, so this is what we have, okay? And so what I'm going to do is we can replicate this, and we can say run this 10 times and see what we have. So we won, lost, 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 won, lost, won, and then we doubled down and won, and that happened to us twice in a row. So that was pretty exciting. Okay, we can here I'm doing it with verbose equal to true. I'm only going to do 3 replicates, and we can see exactly what the thing is doing here. Okay, we can see exactly what kind of optimal strategy is being implemented here. Okay, so here now I'm going to run this, and we're going to just start off at this arbitrary seed here. And here we're going to look at the wins that we have. We're going to replicate this 1,000 times playing the optimal strategy. Okay, using the same initial seed, we're going to replicate our strategy 1,000 times using the simple strategy. Okay, and just let's see what happens. Okay, so we do win optimal. Okay, and we can kind of just get summary of win underscore optimal. Right, so the average loss there is -0.0325, so we're losing 3 cents on the dollar every time we play, with a median of 0, which is kind of what we expect. We can compare this to the simple strategy, summary of win underscore simple. All right, and so with our simple strategy, we have kind of an average loss of about 5.6 cents on the dollar. So so the optimal is a little bit better, right? And we can create a plot kind of showing this. Let me just zoom here, right? And so this is you guys know density charts, right? Okay, density plots. And so we can see with the simple strategy, either we come out ahead with we lose with -1, we push with probability around 0, and then we win with 1, and sometimes we'll get 1.5. Okay, with the optimal strategy, losing happens a little bit less and winning happens a little bit less, but we can double down and win 2. We can also double down and lose 2, and things like that. Okay, so we see little peaks here around 2 and -2, and splitting and things like that. So we have a higher probability of winning one and losing the other, or something like that. So we can see kind of the density chart being a little bit different when we implement our optimal strategy. And then again, the mean for the winning optimal and the win simple is just ever so slightly different. But if you're going to play lots of games, it could make a difference, right? So after 1,000 games, this is a loss of what, $33, and after 1,000 games, this is a loss of $56 times your bet. Okay, so I don't know. That's if you're playing $1 blackjack, which doesn't really exist anywhere. But and who's gonna play 1,000 hands of blackjack, right? So, but who knows? Who knows? I don't know. You guys ever? I don't know. You guys go to Vegas and play games? I always tell people I teach statistics, and then the first thing is like, oh, do you count cards for at blackjack? And the answer is no. I like to roll dice. But no, it's just pure random chance. The only thing you should learn is the less you play, the less you'll lose. Okay. we can do we can create a payoff function, which basically just calculates kind of the mean of the results and the standard deviation and the median. Okay, so all payoff does is basically does exactly what we did here, where we ran the function replicate. Okay, except we're going to do this. Okay, and so what this is doing, so we are going to we're going to run payoff here. Okay, so payoff is this thing. This says if you sat down and you played 1,000 games, this is what you get. Okay, so here let me just do payoff. If I do payoff 50 strategy simple with our shoe, okay, after 50 games I came out with actually dead even. Okay, here I played another 50 games and I came out a little bit ahead, okay, with an average game. Here I played another 50 games and I came out behind, okay? And so the idea here is, the difference here is that here I'm only playing 50 games, but I'm gonna replicate this 1,000 times. So the first time I did it was, if I sat down at the casino and played 1,000 games, what would happen, okay? Now I'm gonna say, I'm gonna go to the casino and play only 50 games, but I'm gonna go to the casino 1,000 times. And we'll say, what's gonna happen if I have 1,000 sessions of 50 games each, okay? So this is what we have. We're replicating payoff here, okay? And we have it for the simple strategy versus the optimal strategy. So if I go to the casino 1,000 times, each time I play 50 games using my simple strategy, okay? It takes a little while to run, but it's done, okay? And then now I'm gonna say I'm gonna go to the casino 1,000 times. Each time I'm gonna play 50 games using the optimal strategy, okay? Again, it takes a little bit of time to run, but it finishes, okay? And you know, if we had more time, you could do 10,000 visits to the casino, 50 games each or something like that, right? Because that's more likely. You're unlikely to sit at the table and play 1,000 hands. You're more likely to play maybe 50 hands or less whenever you run out of money and you say, okay, I should stop playing. But yeah, you might start off with, like, say, I'm willing to play $200 worth of games or something, and then who knows, maybe with a streak of bad luck you lose or something. Okay, so we have now 1,000 visits of 50 games each under simple strategy, 1,000 visits under 50 games each using the optimal strategy, and we can see we'll put them together in the data frame, and then we'll make a quick plot here. Okay, and so this is kind of the density thing. And so with the optimal strategy, so this line right here, maybe you can't see it, we can see the optimal strategy after, you know, when we play 50 games, we're a little bit more likely to come out ahead than we are using the simple strategy. So with the simple strategy, you know, we're ending up behind a little bit more often, okay? So this is, I don't know, there you go, okay? And then we can kind of just see, yeah, if we take our data frame and we ask for the summary on the data frame, so, oh no, this is not. Group by to load duplicate. Okay, so we'll take our data frame, group by strategy, and then we'll do summarize. Okay, and so after 1,000 visits of 50 games each, our average takeaway is that with the optimal strategy, we actually came out a tiny bit ahead after 1,000 visits. Each of those visits, we came out with 1 cent on the dollar ahead, and then with the simple strategy, we came out behind about 6 cents on the dollar for each of those 1,000 visits, which yeah, you could. So anyway, that could be partially due to luck. Well, it is, but yeah, the optimal strategy is better than the simple strategy here. Okay. Now, with our leftover time, we can talk about starting to count cards. Okay, and so we can count cards using a reference class, right? And so here's some code to kind of demonstrate how reference class goes, and this is code taken from the chapter. Okay, but here we'll just go straight to here in implementing the shoe using a reference class, right? So the key thing about reference classes is that reference classes are mutable in that when you change the reference class, it stays in effect, right? Rather than in other cases you make copies and things like that. Here we can kind of keep track of something, which is good in the case of dealing cards from a shoe. Okay, because earlier the way we implemented drawing new cards was we're drawing from a deck of cards with replacement, which is not entirely accurate, right? It's, if you have like 100 shoes in the thing, it kind of acts like you're dealing with replacement, but the idea here is that here we've got a maybe 6 decks in the shoe, and we're dealing without replacement until we get to about 1 deck or less remaining. Okay, so here this is we're creating a shoe. The shoe is going to have several fields here, which will be the number of decks, all of the cards. We're taking all, like if we have 6 decks, we're going to take all 312 cards and shuffle them and just create kind of the arrangement of all 312 cards. And then we're going to keep track of where we are using the position, okay? And so rather than physically dealing the cards out, we're going to just say here is the 312 cards in our shoe, and then we start off at position 1, and we can say, okay, the first 2 cards go to the player, and then the next 2 cards go to the dealer. Okay, and then so for the next hand, we're going to start at card number 5. Okay, or we update our position to start at card number 5, and then so for the next hand, we can say, okay, the player gets the first 2 cards, or if he hits the next however many, and then we just update our position that way. Okay, and so it is like having the shuffled deck, but then you're just dealing out the cards by just updating the position and moving down that sequence of 312 cards. So we have position, and then debug. This is going to be true or false, and this is kind of like having verbose true or false, telling us messages that might be helpful for us. Okay, so we have a few methods. The methods are shuffle, which will be we call the function shuffle decks. If you recall that one was just taking all of our decks, shuffling them up, and that's going to return our entire vector of cards, and then we update our position to be at position 0. Okay, and then draw n is we're going to just take the drawn cards will be specified as cards at the current position plus sequence length n. Okay, so sequence length, so sequence underscore length, if you do 10, will be basically 1 through 10. Okay, so it's going to return back cards at position. If we have position 0, it's going to return cards 1 through 10, or position, if you're starting at position 55, it will return cards 56 through 65, so on and so forth. Okay, those will be the cards that are drawn, we update our position by adding n to it, okay? And then we just have, you know, if the number of decks that you have is less than or equal to 1, okay, and then shuffle the cards. So generally, yeah, at Vegas, they start off with a shoe of 6, and then they put kind of a marker in the deck or in the shoe, and when they reach that marker, then they know it's time to shuffle the cards. Okay, decks left will be a function of you know, the decks minus the position over 52, and then played will be all of the cards that have been played so far. Okay, so sequence length, right? So if you were at position 200, okay, we have the numbers 1 through 200, and played will be, you know, subset, return back cards 1 through 200 in the vector of cards. Okay, so these are all of the methods that we have for this shoe. Okay, and we'll create a new shoe by saying, okay, we're going to start off with default with 6 decks. We'll have debug turn to false, and then we'll start with this many decks and things like that. Okay, so we do that, and so here I'm going to create a new shoe. Whoops, new shoe with 3 cards or 3 decks, and so here I can ask for my shoe, and so here we can see the 156 cards or whatever. We're starting off at position equal to 0. Debug is true. So if I draw 12 cards, this is what I have. We can see these are indeed the first 12 cards that I have. And then my position is now updated to 12. Yeah, I've got 2 decks left. Okay. Let me just go back and I'll draw another 12 cards here. Okay, so notice, or maybe I'll just draw like 3 cards. So here, these were the first 12 cards, and because I've got position here, I can say draw another 3 cards, okay? And then we'll draw these ones, 10, 10, 1, okay? And then I can say, okay, what is my position? I'm now at position 15, okay? And so if I draw more cards, it knows to start here. So we are dealing with now a finite deck with actual positions stored in memory here. Okay, and then we can see, you know, if you draw a whole bunch of cards, okay, you know, this is what we get. You know, my position's now at position 52, and if I draw a whole bunch of cards and I say, you know, what's my position, and ask how many decks left, it says there's 0 decks left, and so the next time I ask to draw cards, it'll say I've got to shuffle the cards now. Okay, so it doesn't run out. Okay, so we'll create a new shoe with 6 decks in it, and now we can play. So let me just show you what my shoe looks like. Okay, so here are the cards stored in my shoe: 7, 10, 5, 10, 4, 4, 6, 10, and then we can see, all right, let's play 3 hands. Okay, we're going to replicate hand 3 times, okay, and we can see where those cards went: 7, 10, 5, 10, 4, right? 7, 10, 5, 10, 4. These are the cards that show up from the actual shoe, and so we can see based on what we've seen. Okay, you know, we've dealt out this many cards. You know, now that we have, you know, cheater mode enabled, we can actually see the next cards that are going to come. So if I draw the next ones, I know, you know, we got 10, 4, 3, 1, 10, things like that. Okay, I'm sorry, not 10, 4. The next ones will be 4, 3, 1, 10, 6, and so on and so forth. And so if I say play hand, let's just do 1 hand here. We can see. Yeah, 4, 3, 1, 10, and 6, and so on and so forth. And we see that indeed the shoe, now being a reference class, is keeping track of all of this. Okay, so we have all of this, right? So our strategy here is using the optimal strategy. Okay, so now we want to try to implement our card counting system. So the way card counting works is we don't, there's all sorts of methods for trying to outsmart Blackjack, outsmart the casinos at Blackjack. And one is, which is what we're gonna try to implement here, is keep the original strategy of hitting or staying or whatever, stick to the optimal strategy as defined in that table. And what you do to come out ahead or not to come out ahead is you change the amount you're betting. Okay, if the count is good, increase your bet, and if the count is bad, just play the minimum bet. Okay, and the idea being cards that increase the count are, quote, bad cards, right? Have you guys heard of the movie 21 or something? Okay, basically he summarizes the thing. And basically cards 2 through 7, if they show up, they're considered bad cards. And so if they get dealt, that increases the count in the remaining thing, right? Because you don't really want to be dealt 2 through 7, okay? Tens and aces, okay, are good cards. So if they get dealt, what remains in the shoe is not as good. So the count goes down, okay? And then everything else, so that would be the 8 and the 9, those don't affect the count. Or did I count that wrong? Everything should add up to, maybe 2 through 6, okay? So what I have here is we have a function called high-low. This is the simplest counting method, and this will return the count of the deck, okay? So let's say if I do, let's start off a new shoe. Okay, we're gonna do a new shoe, and then we're gonna play 3 hands, okay? And so if I do my shoe, $ position, we're at position 19, and if I ask for the function played, this returns the first 19 cards in my shoe, right? So my shoe, these are the first 19 cards, and we can ask my shoe play. These are the 19 cards that have been played, okay? We can ask the high-low count, and what this does is that using subsetting, it's going to say, okay, if it's an ace, give it -1, 2, 3, 4, 5, or 6. Add 1 to the count. 7, 8, 9 don't affect the count, and 10s also bring down the count. Okay, so basically, if I take this and so this is a vector of length 10, and I say my shoe $ played, okay? No, I'm sorry. Here it assigns the count for each of these things, right? 3 is a 1, 3 is a 1, 9 goes to 0, 9 goes to 0, 10, -1, 10, -1, and so on and so forth. So we can see how each of the cards that get played, you know, by indexing the thing this way, we can get this, okay? And so what the function here does is basically it just takes this and it adds them up. Okay, so currently the count after these 19 cards have been played, the count is at -2. Okay, and so that's all that high-low does. Okay, so we could just say, okay, high-low, and we're going to say this is a function of the cards that have been played. Okay, and it says the current count is -2. And as the game goes on, as we play more hands, we can ask, okay, well, what is the current count now? Okay, after additional hands, the count has changed to be 4, and so on and so forth. Okay, and so based on what this returns, this can affect the way we affect our bet. Okay, and so what we'll do is we'll take a function creating a bet based on the count, okay? And we'll do this, and okay, and then and so now that we've implemented the card counting system, and we can keep track of the count of how many good or bad cards are left in the shoe, we can then implement kind of our strategy. And so let me see if this will work. Okay, so we have a bet function, and we'll, okay, that's fine. Okay, and so here we are going to calculate the gain, and what we're going to do is, you know, with regular we will, you know, we just kind of bet the same every single time, but with the strategy of counting cards, we can change the bet based on the count in the card, okay? And so here, we're just kind of doing this a little bit quickly, is we'll create a new shoe. We're going to play, you know, 1,000 games, and 1,000 visits to the casino with playing 50 games each, right? Let's see if this works. So it's taking a little while to run. Maybe it didn't work. Okay, it ran. All right, so payoffs. This is what we have. We've got all of these things. Okay, and let's see. Okay, so we actually got lucky in that we came out a little bit ahead, and then using the card counting method, we came out even more ahead, okay? Whereas if you look at the standard deviation using the card counting to affect our bets, the standard deviation of our winnings is much higher in that because we're betting a lot more than just the same small bet every single time, okay? And we can kind of see, you know, the difference between all of these things and whatnot. So let's. So this is kind of the difference in gain between. So this is a little bit. Yeah, I don't know. Maybe it's not that great. But basically, it just says after in 50 bets, you know, a lot of times there's not a whole lot of difference between the fixed betting strategy and using the card counting system, but I guess if we look at it, we do come out ahead a little bit more often than not, okay? I'll have to double check all of my code and make sure it's correct. But, you know, I thought this was an interesting application of computerized simulation, okay? This would be, you know, trying to do the math behind an actual card counting system. It would be very, very complicated. Now, admittedly, programming it was not super easy either, but I do think that the simulations do allow you to do things like, you know, what if I only want to play 50 hands versus, you know, playing off to infinity or something like that. And so computerized simulations allow us to, you know, get an idea of the answer to these tough questions without having to do the actual math, okay? And in a lot of cases, you know, using a reference class and whatnot is helpful. So, you know, if you have the time, definitely read through this chapter written by Hadley Wickham. It's very good, good stuff. And you know, I'm gonna give you guys a homework assignment where you're gonna do some simulation yourself, okay? And so, so you have that to look forward to. So we'll end here for today. I do have office hours, and I'll be happy to try to field your questions there. Okay, good luck.